All right. So I think I've posted the recorded lectures for the metal additive manufacturing. I don't know if you have the chance to go through the videos, but what I want to do today is to quickly go through the lecture. And if you have any questions, just let me know and I can answer the questions for you. All right. I think that's the we only have I think two topics left after complete the metal additive. One is the sheet lamination additive manufacturing process. Another one is the some mechanical elements for 3D printers, which consists quite a bit those commonly used sensors, electrical, mechanical components for 3D printer. And I think other than that, there's not much content left. So pretty much, I think 1 or 2 lectures, we will complete all the lecture sessions. And so let me check the calendar. So we will have a break during the Thanksgiving, which is, let me check the RIT calendar, which is November 24th through 24th, no class, and November 25th, 26th, Thanksgiving holiday. So that is okay. That is Wednesday through Friday, but still we will have Monday class 22nd in that week. So we have pretty much time, quite a bit time in this month before the end of this month. And I'm thinking of to have a presentation about your final project in the end of the month, probably 29th or something. Yeah, I think 29th would be a good time for us to have a presentation. So how do you think? Any problems for that day? No? Okay. Yeah, then I will tentatively set up 29th as the day for the presentation of your project. And originally we have 3 exams, and I realize it could be merged to 2 exams. We had 1 midterm, and so then we will only have another final, and that's it. That's the 2 exams. So that will happen in the last week of the exam week. Oh, by the way, I will post the grades for all the homeworks you submitted. Except homework 4, I haven't completed that. Also, I will post the midterm grades probably by Tuesday, tomorrow, and I will post all the grades. And we can have little time. If you have any problems on your grade, you can discuss with me in this week or next week. All right. Anytime you want to make an appointment with me, just send me an email and we can discuss on it. All right. Any question? Nope. Okay. So let's start the lecture, and let me quickly go through the metal additive 1, 2. So in the first lecture of metal additive, we had a understanding of this RC emerging technology, which based on the magnetohydrodynamics. And it is a liquid metal jetting based process. So it's quite similar to the material jetting. Instead of a plastic or polymer powder, in this process, the liquid metal particle is jet onto the print surface, like the one shown in the illustration figure. Basically, there is a coil shown here, and the current through the coil will produce a magnetic field that will introduce the eddy current in the metal, molten metals. And basically, the magnetic field, the electric field, they are coupled together to result a Lorentz force, such that will push those liquid metal particles onto this printing platform. So that's
Professor,
yeah.
Professor, are you sharing your screen?
Oh, I didn't? Oh, sorry about that. Yeah, sorry. Let me just share my screen. How about now? Can you see it?
Yeah.
Okay. Okay, good. So that's the basic working principle for the VADAR system, magneto hydrodynamics based liquid metal jetting. And some of the benefits, right? Why we still need this? Because there are already there have been already quite a bit process in the, sorry about that. Let me mute my phone. Quite a bit metal printing process existing, but still we need this process. The reason is, well, the cost. If you check those powder-based process, the cost is pretty high compared to the material used in this process, which is the metal wire. And also it's much easier to use because this process does not require much handling time, right? For the powder, you have to recycle the powder and mix the powder and clean the powder off the prints and so on and so forth. Another thing is the printing speed, efficiency, right? You could have multiple, because I mean this the printing the mechanisms for the printer is pretty simple, right? It's just those jetting nozzles, right? If you have one jetting nozzle, you could easily scale up to have multiple one. And also no need to consider about the powder loading, cooling, and unload, and so on and so forth. It makes the printer simple, reliable, easy to use, and also a high efficiency. These are all the possible benefits from this process. So I think you have you can check the video yourself, but we have one printer in the Brinkman lab. If you have the tool in the beginning of the class, you will see that printer over there. And it's still under research, right? It's not a fully ready product. Basically, the aluminum wires is used in the printing process, right? Here shows some of these parameters. So also the process, as I mentioned, there is a magnetic and also electrical field utilized to drive the molten metal during the printing process. So you can see some of the videos when the material is jet, and some of the effect for the frequency and separation distance for the droplet. and how this will affect the printed trace. As you can see here, the lower frequency will lead some disconnected regions for the trace. On the other hand, if the frequency is very long, there could be a possible extra material jet onto the printing platform, right? Also, if you control the droplet separate distance, usually higher distance will, larger distance will produce I would say, this sparse droplet distribution on the printing platform, and vice versa, right? It's kind of, you have to balance these two to make sure the best quality trace will be printed during the printing process. And if you have some zoom in view and see more clear about those droplets, right? You will see there will be a difference if you control control the spacing and as well as the frequency, right? So by combining the different conditions of spacing and as well as the frequency, you can find some best quality prints. For example, this one, probably this one, right, will be something you would consider about. I would say this one probably the best quality you could achieve by setting up a 0.05 millimeter spacing and 67 hertz as the droplet frequency, right? So this is the design of the experiment. You want to find some parameters and do some samplings in a range for those parameters, and make sure a combination of all these sampled values of the parameters. And it turns out you will have a span of the parameter space and versus some printing result. And among these results, you will find the best one. That is how you determine what kind of parameters you should choose. And the key for this kind of process is you want to figure out what are the important parameters. I think that's the most challenging part for the whole process, right? That could be too many parameters for one process. So what are the most important ones? What are the ones you could think of to do the experiment based on them? So this requires basically the experience as well as the fundamental knowledge of the process, right? Also, I mean, just one more, some add-ons. There are some new computational methods based on artificial intelligence algorithms like machine learning, deep learning. So they are utilized to determine what are the key parameters for a process. The reason is, as I mentioned, there could be too many parameters for a complex process. And sometimes it's just too challenging to figure out by human. So how about we feed those parameters and versus a result, and to figure out a correlation between them. And also you could find the weight for each of those parameters. And turns out you will have a better understanding of which parameters would be the most important ones or the key ones, right? That's some new development in this design of experiment. Also, other parameters like the temperatures, build, platinum temperatures and all versus the jet frequencies. So again, you could find, well, which ones are the best for, which are the best combinations of these parameters, right? Sorry. For the jetting, what you could do is basically you have a mass per droplet and the density of the metal, right? Then you could have a and also a jetting frequency and the desired width and height of the printed track, like the one shown here. Basically, you can imagine a trace is something like this, right? Turns out you can compute the printing head velocity, which is you need to specify to control the printing head during the process. So what you want to do is, well, basically you want to have this is the printing head velocity, and what it look like is for each of the in each of the second, there will be a droplet number, and that's the jetting frequency. And you can consider each of the droplet to be a sphere, right? And you can use this equation to compute the volume of each of the droplets, right? And then that's the one droplet. So how about you have all other? How about you want to have the length of this trace in for a 1 second, right? That is use this volume to over this width and height. Then you will have a length for this trace, and that is what you want to figure out the velocity. So basically, maybe it's a little messy, and let me erase to give a better explanation. So basically, this part will compute for 1 second what will be the volume of the material, the printing head jet. And that's the overall material volume. And as we assume on the printing platform, a pattern like this, a trace like this is produced. Basically, you have a width and height, also a length, right? And if you compute in 1 second what is the volume for this trace, then you could easily compute what is the length in 1 second the material is jet onto the printing platform. And what you essentially do is use this overall volume to over the width and height, right? The production of width and height. And turns out you will have the length per second, and that is a speed. So in 1 second, the printing head will travel that amount of distance. And that's how you compute the printing head velocity. Any questions for this computation? All right. So also you have known the velocity and what is the drop spacing. So basically, that is how you compute. Basically, you have to think of how the frequency, jetting frequency, is related to this drop spacing. So as you can see here, this drop frequency tells you in 1 second how many droplets it will be there on the printing platform, right? And that's what the frequency jetting frequency tells you. And then you know in 1 second what is the distance it travels, which is the printing head velocity. So you know in 1 second the distance the printing head travels is v, and also in this distance there will be f droplets jet onto the printing platform. Then what's the distance in between of this droplets? So basically you use this v over f, then you have the droplet spacing, right? That's how you come up with this droplet spacing. Another thing is this overlappings. If you know the droplet diameter, what is the drop overlap as a percentage of the diameter? Basically, there could be a 100% overlap, like the one showing here, which is one extreme, right? And another extreme is there's no overlap at all. And that is what you have like this. So basically, that is how you compute. If the distance between basically if the distance between the two center of the droplet is 0, that means there will be a 100% overlap. If the distance is greater or equal to its diameter, that means there's no overlap at all. And through this, you can tell what is the percentage, right? Like the one shown here. Yep. So the thermal control is another very important thing for the metal printing, especially for the microstructures. And a rapid solidification of the bottom, at the bottom of the droplet, and a slow cooling at the top will give you a distinct grain size and the interface. As you can see here, this shows a very clear interface for the grains. And that is because the the sequence of the solidification, right? So in that sense, you do not want to generate such kind of an interface, because usually this kind of interface will be the weak point for the structure. So how to kind of overcome this? And that requires a little kind of a thermal control, right? Basically, you want to control the temperature during the printing process and make the heat distribution more evenly, such that such kind of interface will be minimized, and the structure of the metal prints will be better, and the mechanical property of the prints will be much better. And some of the aluminum alloys, right? You have different elements to be combined for different aluminum alloys, right? And also there are two 6061 and 7075 alloys, which can be processed using the jetting-based process, and could be difficult or impossible through the powder-based ones. And again, that's another benefit, right? And particularly this 7075, it has a high strength, and the weight is light. Also, for some of the applications in aircraft, it has a widely adoption in such a process. And it prone to stress corrosion cracking. And that's another good property for this process. And that's why this material is under the focus. So yeah, I think you can just look at this macroscope picture. And here shows the build direction. And you can see there's no visually significant interface or some boundaries. If you look at the layers, that means it overcomes the problems what I mentioned for the clear interface between the different grains due to the thermal control problems, right? And if you compare its microstructure with the one casted using the casting process, there's no significant difference between the two, right? And I think you can quickly go through this. Here's another experiment for different spacing and pilar angles, right? And some lattice structure could be applications for this process as well. You can check the video yourself, right? I think that's a quickly going through of the metal-based, I mean the liquid jetting-based metal printing, and we can look at the another one as well, which is this one, the powder-based, which is the mainstream printing, metal printing process. If you check the energy beam to solidify the powder, you will immediately realize there are two different types. One is the laser, another one is the electron beam. These two are the major power source for the energy for the metal powder prints. And you can see a dramatic increase, in the metal printing. Actually, it's the metal powder sales. And that indicates, well, there is a increasing in the consumption of the metal powder, and also the increasing popularity of the powder-based printing process and machines. So there are some different process you should look at. Direct metal laser sintering, direct laser metal laser melting, selective laser melting, and also the electron beam meltings. And these are the some of the main processes, as well as the some of the acronyms. So the selective laser melting is one of the most popular ones. What it does is it melts the powder using a high power laser, and that's what it does. If you look at this video, you will see it's quite similar to what we have learned in the selective laser sintering process for the plastics powder. But in this one, it's the metal powder, and instead of sintering, it is melting. In other words, it has a high temperature and higher power during the printing process. Here shows you a part built by the process, right? And basically the strength of this process is it produces the parts with a high density. Also, the resolution is pretty high, usually 0.02 millimeter for one layer, right? That is a really thin layer. And turns out it will make the part with a very high accuracy. So another thing is it also have some drawbacks which need to be overcome. For example, the high thermal stress, because the printing process basically there's no preheating for the powder. It's a cold process, so that will be the thermal stress produced during the printing process, and that could kind of degrade the mechanical property of the parts. A second one is the printing speed is slow, and also you have to control the atmosphere for the printing process, which could be troublesome. And that's the pro and cons for direct metal laser sintering and melting. So the powder is the key for such a kind of process. And you want to look at the powder spreading during the printing process. And first of all is the blade could have collisions when spread the powder during the process, especially when one layer is print, there will be a spreading step added. And because the printing accuracy, because it's not a, I mean, you cannot achieve a 100% accuracy, right? That means that could be some inaccuracy on the parts, and that could cause the collision between the blade of the spreading roller as well as the printed parts. If that happens, to avoid a interruption of the process, the blade need to be flexible. In such a case, even there's a collision, even there's a little collision, I would say, of course, it cannot process those. I was a very, I mean, if the parts has some problems on the platform, I mean, in the printing bed, and is tilted, let's see. And there will be large area of collision between the parts and the blade. Of course, in that case, this cannot be handled. I mean, that probably there will be some detection and the machine will be stopped. But if not the case, if the collision is just a smaller one, tiny one, because of the printing accuracy of the parts, in that case, a flexible blade will help, and that will continue this spreading of the powder and will not interrupt the whole process. Another thing is basically a roller, a rotating roller is used to smooth the surface for the spreading of the powder process. All right. Again, the recycling. We have talked about this in the selective laser sintering process for plastic powder, right? So for the metal one, you have to recycle the unused powder because it's so expensive. I mean, it's not affordable if you do not recycle them. So the recycling of unused powder is a must. For many applications, the lot traceability would be essential, especially for the aerospace, biomedical, as well as some defense-related applications, you really want to have a very tight traceability for the parts to be printed. And these are the essential thing for this process as well. Some of the equipment and look at some of the trends for the equipment. Let me move this somewhere. It's a little annoying. All right, maybe here. Yeah. So of course, a larger printing area would be preferable. That means you can produce a larger parts. Another thing is the automated powder handling, right? How you handle the powder easily and automated. That's another trend for the equipment development. Again, the efficiency would be another important thing to get improved. So the process control, monitoring, the error case notification, as well as a more user-friendly interface between the machine and human user. These are other factor or the directions those manufacturers and researchers are looking at. Sorry. The parts, I mean, the components of the machine are desirable to have modularized parts, such that if the machine has something wrong for some of the components, you can easily replace those components instead of having too much involved for the whole machine, right? So some of the examples for the printing using the metal powder-based process. One thing I want to put some more words on is such kind of weapon. I mean, actually this caused some concerns, especially when near like 2014, 2016, 2014 through 2016, there are huge concern about the printed weapons because there are some events, some incidents, basically someone print guns or other weapons using 3D printer, and that weapon functions properly. And there's not allowed. And because this kind of design of weapon is open source, you can find it. And even not a metal one, even some polymer parts, and you assemble them together, the final weapon would function as well using those polymer or plastic parts. Although it cannot last long time, but overall it functions. So that caused a huge concerns. And from a different stakeholders. But what I want to say here is, well, definitely that requires a regulation as well as a kind of technology to kind of prevent such kind of cases, right? For example, there are some research. Basically, they integrate cameras onto a printer, and also they write some object recognition method and integrate them into the chips of your printer. Turns out it somehow understands the parts is being printed. So for example, some of the parts are quite unique for weapons, not necessary to be these larger parts, even some of these parts, or even just a screw, it is unique. And by identifying these parts, even small ones, using some machine learning based object detection method, it has a chance the printer will know, well, the parts to be printed has something wrong, right? Could be part of the weapon, and the printer will refuse to print the parts, will notify the user, well, there's something wrong, probably you can print it, or requires authorization. I mean, only it is authorized, the printer can produce it. So this is basically an example that technology help to solve those social problems. And well, that's a very interesting example. I mean, similar object detection method is utilized in the security check when you go to the airport or something. Even by the X-ray pictures, the algorithm will recognize the object or even some parts, components. Like as I mentioned, even those small ones, it is sufficient to determine whether this object is related to something which is inappropriate to be taken into the airport or some important place. All right. So let's look at the effect of thermal stress. As you can see here, this part, this surface is supposed to be a plane, but as you can see here, there's a bending, right? And that is the example of the thermal stress in the process. So you might be interested in how the parts to be removed from this platform. Basically, there's a process which will use a wire to kind of cut off the parts from these plates. Here shows this process. And as you can see here, the wire is fed through this region, and that will be used to cut the parts, and eventually you will have the printed region obtained. Sorry. Another process is this electron beam melting, right? Again, the power source is this electron beam. And as you can see here, the electron beams is ejected through this region, and the focal length is utilized to guide the electron beams, make sure it will be focused onto the spots I mean, on the printing platform. And turns out one layer will be solidified by using this electron beam energy, right? And again, a full density metal part could be produced. And it is a hot process. Means in this whole region, the powder bed need to be heated up such that during the printing process, the temperature difference between the environment as well as the parts, I mean the powder, will be minimized, and the little thermal stress will be introduced. Sorry. And another thing is the fast battle process speed compared to the directive laser melting, right? So there are some drawback as well. First of all, it has to be a vacuum chambers. The reason is the particles, I mean, other particles in the atmosphere could block the electron beams could be defocus the electron beam. In that case, you have to make the whole region to be vacuum. And the material is quite limited. And that's another reason. Because of this process requires the utilize the electron beam to melt the metal, and not every type of metals could be melt using the electron beam. So that determines that there will only a few commercial available materials to be utilized in this process. And as you can see here, it produces really nice parts, right? Again, let's check the video a little bit. So as you can see here, each of the layer is solidified, and the material is spread onto the newly printed layers, and turns out you have the whole parts. Right? Quite similar to other printing, I mean powder-based. And here are also quite a bit examples in the printing. Again, the blade for spreading the material is desirable to be a flexible one. That will again prevent the collision between the printed parts and also the blade. Similar reasons, right? Because of the inaccuracy of the printed parts. Here shows a electron beam guns, right? It's similar to the electron beam guns in the old TVs, right? But the power is much higher in this case. Basically, there's actually no motion, no actually moving parts. The electromagnetic deflection coil utilized here will steer the direction of the beam to the desired location. This is pretty fast. This sorry, the steering using the electromagnetic deflection. So, and that's part of the reason for a high-speed process. As you can see here, this steering can achieve like 100,000 meters per second, which is really fast, right? Also some amalgam patterns, right? As you can see here, the beam traces the contour, and also it will melt the interior region as well. And you can rust all the ways from side to side, and you can melt the smaller squares as shown here. So these are the some of the patterns the beam could travel. Material, very expensive powder. And basically, as I mentioned, there are quite limited choices for these powders. That decide the EBM is utilized for the applications which requires a near net shape parts with complex geometry, or the weight reduction is critical. So in other words, some of the defense applications, aerospace, airplane parts, and so on. So another thing is the electrons from the electron beam must have a place to go when they strike the surface of the part. And in that case, this process can work well with those electric conductive particles. On the other hand, the plastic powders is not applicable for this process because the charged particles repel one another in this case if the electron beam hit onto the surfaces. And that's why the metal ones can be used and the plastic ones cannot. So some of the discussions. Basically there are two powder hoppers on both sides of the printing platform, and that will kind of half the time for spread the powder onto the printing bed. And again the vacuum, that is because of the electrons will hit the gas molecules, and that will make the electron beam lose the focus. And that's why the electron beam systems requires a vacuum, but laser does not. Laser-based does not. And the preheat. Again, preheat will reduce the thermal stresses, and that will reduce the thermal distortion as well for the parts. And another point here you want to pay attention to is the powder around the part are partially centered. The reason is to improve the electrical conductivities of the powder, because the centered powder has a better electrical conductivities. And before the powder to be cool, you do not want to open the door, since the whole chamber is a vacuum. If you do so, meaning open the door before the powder is still in high temperature, the powder will oxidize immediately. And be aware of this. You do not want to open the door before the powder to cool. And another thing is related to the monitoring windows for the machine. So during the printing process, there will be a X-ray generated, and the window need to be made of leaded glasses, such that that will protect the user from the X-rays. Sorry. The spreading blade again is desirable to be flexible, such that that will allow some part slightly distance of the parts without a collision. Another thing is the excess powder reuse, right? How you reuse those powders, and how you remove the powder from the parts and reuse them. So that requires a blasting process. And in the blasting process, the same kind of metal powder is utilized to remove the excess powder on the printed part. And that is to avoid the cross contaminations. And the last thing is a minute amount of helium gas is fed into the chamber over the powder bed. And why you use such a gas? Basically, that will neutralize the charge, because you are talking about some electrons during the printing process, right? Definitely you want to neutralize them. So this equation is very important, and that represents the heat input. If you check this equation, there are several parameters like Z, the melting depth, beam power, temperature rise during the process, thermal conductivity, diameter, velocity, density, and the specified heat capacity, and so on. So by plugging all these necessary parameters, you can tell what would be the melt depths for the process, right? If you have known all these values. So that could be an example if you want to compute the depths of the melting pool. And basically these numbers are given, and it turns out you can so you can do the computation by substituting these values to the equation we just showed. One thing you want to be aware of is the density utilized here. So the solid density of the material is this alloy is this amount, right? 4.42 gram per cubic centimeters. But we are talking about some melting powder. That means probably it's lower than this density for the melting powder. And what you're gonna do is to figure out the melting powder's density, which is some percentage of the solid density. And in this case, we use 0.64 as the ratio. And you will have a melting powder density like this, and use this to do the computation. All right. And again, to make sure these units is the one you need by checking this requirement, right? And do the necessary conversion such that these units are the one required. And then you will have your number, which is this, right? That's how you compute the melting pool depths. So another point here is the vaporization of the alloy elements. So for the alloy, for example, this 7075 aluminum, there are different elements. So during the printing process, there could be some evaporation happens because we are talking about a very low air pressure. I mean, almost vacuums, and there's a thermal energy generated. So in such a condition, there could be some evaporation of some of the elements. So how you determine there will be a evaporation or not. If there is, well, that means that material is not applicable in the process because some of the elements would be vaporized during the printing process. So it is essential to determine that before you decide whether to use the material or not. So in that case, you want to check for a chart by looking at the temperature, the alloy, and also the vacuum. I mean the air pressure. So that is something like this. Basically, it gives you the vapor pressure curve of the elements, right? And here you can see these are the different elements, right? And also the horizontal axis is the temperature. The vertical one is the vapor pressures in torr. And basically, given a torr value and temperature, and also given certain elements, you can find a dot, right? For example, you have in this case, it's what is this? 1,000 Kelvin, 1,000 C, and also a vacuum pressure 10 powered by -3, and it turns out you can find what is the element here. It doesn't specify, but let's see, it's aluminum, where it is here. And I don't think it's aluminum, but that's basically what you want to do is, okay, let's see, it's a Zen, okay? It's a 1,000. Then find where it is, and also 10 powered by -3, and basically anything. So if basically if check at this this temperature, what is the pressure, under what pressure this element starts to be vaporized. If it is higher than, I mean larger, if the current pressure is lower than what you have on this curve, that means there will be a vaporization. Otherwise, there will be no such a vaporization, and you can safely use it, right? That's how you utilize this this chart to do some computation. I think these ones are you don't need to put too much attention to, but this chart, this form is very important. Here shows you some processing. I mean post-processing, like the loose powder handling, some of these cleaning, and also so on and so forth, right? Some of the design guidelines for the parts to be printed using the electron beam melting. And yeah, I think pretty much you can take a look yourself for all of these. All right, I think we have gone through the metal prints. And let's have a 10 minutes break. And then we can talk about some of the sheet lamination process a little bit in the next lecture. All right. Let's meet 10:19. All right. All right, let's continue. So for this, let me figure out, find out where it is. So for this this curve, I think I haven't shared my screen, right? Let me share it. Can you see my screen right now?
Yes.
Okay, good. So for this figure, what you want to use is I want to put more word on it. So for example, you have a vapor pressure like 10 powered by -3, and basically what you want to do is, well, let me find a pen. And also you are looking at, let me see the Zn element. And basically you just figure out a straight line at 10 powered by 3 and find the intersection between the straight line and this element. In this case, it's here, right? And what is the temperature in this case? I would say it's kind of in between of 500 and 600. Let's see 550, right? So basically that indicates under such a vapor pressure, the vaporization point for this element is 550. And in that case, if you have a process temperature to be 1000, it is beyond its vaporization point. And that means the vaporization will happen. And that means this processing temperature is not desirable for processing this element at this vapor pressure. So that's how you tell whether the printing whether the process parameters are appropriate or not. All right. So if you have no question regarding this, let's move on. I have another PowerPoint to share. All right. Actually, this is my first time teach this process for this class. Usually, we don't have that much time in the semester, but in this one, I think everything just going smoothly. So we have the time to talk about this process, and let's take a look at it. Basically, this sheet lamination process is very easy to understand. Basically, the material it uses are sheets. It's not like other process. You have to create layer by layer. In this case, you already have one sheet for one layer, and for this sheet, what you could do is you could bond different sheet together and then form the shape by cutting or other process like the laser or other knife cutting to form a contour of the object. And that's one way. Another way is to maybe you create the contour first and then bond the different sheet together. Either way, that's how the lamination process work. That's quite different from what we have learned, right? Basically, in each of other processes, you have to generate the one layer, not just the contour. You have to have the infill created, the in between. I mean, the interior region of your layer. But in this case, there's no such requirement because you are talking about a piece of sheet for one layer. And that's the lamination process. So the most, I mean, there's a very cheap process, which is the paper-based sheet lamination. And the material used here is paper, it's just paper. And for example, this the layer, this LOM process, that is one of the process utilized in the lamination. And the material used here is a white paper with polyethylenes coated on the underside. And what it does is there is a laser cut, the carbon dioxide laser cuts that cuts the contour and then hatch the support regions, right? And the heated roller will melt the polyethylene on the underside of the uppermost layer on the top to the top side of the previous layer. So by repeating this, you could create a object with a height, right? Basically, you attach one layer to another, and turns out you have a 3D object by doing so. And there's a question is there basically the supported region is hatched, right? The reason is you after the prints, you want to remove those support regions, and if the support regions are not hatched, then it's really difficult to remove them. But if they are hatched, what you want to do is you just tear them off from the printed part, right? And that's why you want to hatch the support regions in this process. So here shows you a illustration of such a machine. And as you can see here is pretty easy to understand how it works. And again, just a white paper with the polyethylene coating to be used in the process, which means the cost is pretty low, right, compared to other printing process. I think there's a video for this process. Let's take a look. The laminated object manufacturing. See, this is the way to. This is how you cut the contour, right? And it is heated up to the polyethylene is melted, and then one layer is attached to the next one, to the previous one. And turns out you have the whole object printed. All right. It doesn't show the hatch, but you can imagine since the supported region are hatched, so it's much easier to get removed. So what are the difference between this laminated object manufacturing process compared to other polymer additive, such as the fused deposition modeling, or these optical based, the stereolithography. So what it does in this process is just cut the contour and then bond them together, something like that, right? So there's no infill to be handled, which are the most different part compared to other process. In other process, basically, it not just contour, but also the interior region of that layer need to be handled. But this one, again, just a contour. And the speed, as you can see here, is much faster because, again, only contour to be cut. The material property, well, it's just paper, right? So that means you cannot think of some applications which requires a nice mechanical property or structurality. For this process, since the material used is just a paper, the experience will be the most essential thing, not the material property or mechanical property. And the cost for this process is really low because of the simplicity of the process as well as the material consumed in the process. It's just the paper. So that's some of the points for this process. And another process like the one showing here, the AMCOR technologies, basically what it does is they use the ordinary office paper, not even not even the one in the previous LOM process, which is the paper together with some polystyrene. In this case, just the ordinary office paper. And basically it has a water-based adhesive. In other words, glue, right? Basically it glues the paper together and use a knife cut to cut the contour. Also, there will be a color inject. So you can have color for each of the layer, and which is really easy to do because you're just using a office paper to print on the office paper is a very mature technology, which is what are those paper jetting, those 2D jetting machine does. So it's a very mature and no problem for doing so, right? It turns out it allows a full color print, right? As long as you have the paper color print, you will have this process, a full color print. So let's take a look at this. See, that's how it works. And these are the object printed using this printer. And the process used in the AMCOR machine is very similar to the vinyl sign cutting machines, which are used to create those vinyl signs. And basically they are almost the exact same thing, right? But just repurposed in this printer. And the similarity for this of this process to the laminated object manufacturing is it utilizes paper, and also it will it just cut and bond, right? Basically, it cuts the part and attach them together, right? But the difference is, well, the LOM utilized laser to cut the paper, and the MCore used the knife, right? Also, the MCore achieves a full color print. Full color prints, which is is a very good point to have a inexpensive and fast printer to produce those full color objects. So another question here is the assemblies. Do you think it's easy to make moving assemblies? Actually, the answer for this question is no, because for the moving assemblies, basically there will be a small gap between those movable parts. I mean, the components of the movable region, and since we need to remove those paper after the process. In this case, the gap between each of the moving parts is very small. In that case, it's really difficult to remove the material from such a small gap. So in that case, it's not easy to create the assembly using this process. But you can always argue, is it necessary to I mean, basically you're just looking at some paper parts, right? I mean, is it necessary to have assemblies using such a process to produce, right? That will be a question you want to think of before you create assemblies using this process. Because after all, it's just some papers. The mechanical property of the printed parts is not good. It's more like for the appearance, for the geometry, instead of for those functional parts. So that's one thing you want to keep in mind, right? I think we don't have enough time to complete the following part. I think we can stop here, and next class we will finish up the rest of laminated sheet lamination based process. Also, I will post a new homework for the metal process. And yeah, I think that's pretty much all for today's lecture. Any questions?
I have a question.
Yeah.
So you said the date November 29th. What exactly of the project is due on that date?
That's the presentation.
Okay, what about the paper and the video and stuff like that? Are those also due on that date?
That has no. You basically on that day you just present your work. You can have extra time for the videos, report, and all the rest. I will usually give like another week for submitting that, as long as I have everything before the last day of grading. I'm okay with it.
Okay, thanks.
Mhm.
And how do we get into the lab besides during our lab period to print stuff? Or are we only allowed to print during our lab period?
I think you can get to the lab anytime. Do you have access to the lab?
Well, it's
You-
locked. And
Yeah,
it
we don't
says
have
that we
Slack
can't
access to
enter.
the lab.
You don't? Oh,
No.
okay. Yeah, I will talk to the manager of the lab and make your card available to access the lab. You can get into there through the front door. I mean, there's a side door or the front door of Brinkman Lab. You can get into there through that door. I will definitely talk with the manager and let him to authorize you. Yeah, that I mean, for the past teams, they have the access. I didn't realize this, and definitely I will do it as soon as I can. Yeah. Any other questions? All right, if there's
I
a,
have one more question.
oh yeah, go ahead.
For our car, does it have to be like all 3D printed parts? I guess it's, can we glue things together, or does it have to be like snapped together and whatnot?
Yes, you can choose to glue or snap. It depends on how you design look like, and also the functions. I think the essential thing is it functions, right? It functions as it is. So there's no restriction if you want to glue them.
Okay, so there's no requirement that has to be able to be
No.
like taken apart or anything like that.
No.
Okay, thank you.
Mhm.
I've got one more question as well.
Sure.
The instructions say that we need one part that's optically clear and polished.
Hmm.
How do you suggest we do that? I'm assuming with the resin printer.
Yes. Yes.
Will we be able to have clear resin loaded this week? I know it takes some amount of time to get change the resin out on the printer.
Well, that's a good question. Yeah, I think that could be a problem. I didn't realize that could be a problem. I probably will remove that requirement. I mean, as long as you have some parts printed using the resin, that's fine. I mean, also, I mean, it has been already included in the instructions. So it's not necessarily to be a clear part, since that takes time, and we might have no such a time.
All right, so it just has to be on the resin
Yep.
printer. It doesn't have to be polished or anything.
Mm-hmm.
All right, thank you.
Yeah, I will change that and add it to the Q&A. And also the one Annie asked, I will add it to the Q&A to make everybody knows. Okay, any other questions? No? Okay, that's all for today's lecture. And thanks for your attention.
Oh, I
Yeah.
forgot. I do have one more question. Sorry.
Oh, okay. Yeah, go ahead.
I know you said that the dimension requirement is 12 inch by 5 inch by 3 inch, right?
Yeah.
Or something, some combination of that. So what if we use the same amount of material that would fit in that, but it's like a little wider? So what if it's like 8 inch by like 8 inch by like 3 inch?
Yeah, I think I have I've posted on the, I don't know if I did or
Yeah.
not, but yeah, as long as it's not too, you have too large, I mean, your design is too large, it's fine. I mean, considering I don't want to let one group consume too much material. It's not
Right,
fair
yeah.
for other groups. As long as you use similar amount of material, that's
Okay.
fine to me. And another thing, again, as long as your part can be fit into the printer.
Yeah, you said the size limit is still 12 by 5 by 3 and we can move it
Yeah.
by 1 inch, but I want to move it by 2, but it's still the same
Yeah.
material and
Yeah.
still fits in the printer. So just wanted to
Okay.
make sure that was the important part.
Okay. Okay. Yeah, that's fine.
Thank you very much.
No problem. All right. Thanks, guys. and see you soon.
Have a good day.
Yeah, you too.